I am poor, but I want to fine tune my own large language model. And you might have heard of tricks like LoRa and quantized LoRa, which certainly allows you to do parameter efficient fine tuning. But did you know that there are more tricks than just that? Me neither. By the way, I'm looking for an internship for AI work, so if you know about anything, just let me know through email or LinkedIn. I need job experience badly. Alright, let's get started. Hello, everybody. Welcome back to my YouTube channel. So, oh boy, it's been a while since I launched a video on YouTube. I've been out for vacation and now I'm ready for work again. And I have some problems here. I try to, you know how LMs need like reinforcement learning to fine tune the parameters such that it has these chatbot characteristics, right? So I was trying to use one of the RL techniques, and here we have the online DPO trainer, and 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 the special thing about the the online DPO trainer is that it is basically an online version of the original DPO algorithm, right? And and not only that, right, but you don't need to have like labels for the query prompts that you provided. So that sounds great, right? And there's and the code is relatively simple, but the issue is that it's really slow to train. It takes like weeks, right? At least according to Py- PyTorch Lightning, right? It takes weeks to train, to fine tune the LLM. Even though if you equip it with parameter efficient fine tuning method, right? So so I was thinking to myself like, oh man, what should I do? Right? Since RL is since reinforcement learning is my only option here, this means that I will have to look for other more efficient ways to make RL go faster. So so I think what would be a better way to do that than to go through every single type of PEFT methods that's available on Hugging Face. And in the meanwhile, I will make a PowerPoint presentation just for that. So, yeah, so in this video here, we're gonna go through every single type of these PEFT methods, and hopefully you and I can learn something about them as well. And disclaimer here, right? I only know about the standard path approaches like LoRa and quantized LoRa, and that's it, right? So I'm going into this fully blind, right? And I'm gonna learn a lot of new things starting right now. So let's see, how many types do we have? I'm not so sure if you can see it. Let me see. Yep, you can see this the left hand side. That's good. So we have Ada LoRa, IA3 Llama adapter, Loha, um, Low KR, LoRa, X LoRa, and so on. And there's quite a lot of them, right? But let's go through the first one right here. Ada LoRa. Okay, what do you mean by Ada? I know what's LoRa. Okay, so Ada LoRa. Okay, this. Let's copy this and paste it right here. So this is Ada LoRa. Okay, so Ada LoRa is a way for optimizing the number of trainable parameters to assign to the weight matrices and layers. Unlike LoRa, um, they distribute the parameters unevenly across the neural network. So more parameters are allocated to important weight matrices and layers. Okay, so it has like a selection bias. Okay, so it's unlike LoRa, which which um treats all or W or weights the same, right? So it is a bias approach in that sense. Okay. Now let's go to the abstract here. It says fine-tuning large pre-trained language models on downstream tasks has become important paradigm. Yep, there's some fluff right there. So yep, and it gets pretty hard, right, to fine-tune them if you don't have like a lot of GPU. Uh, Therefore, many fine-tuning approach have been proposed, right? Such as low rank increments, but they often evenly distribute the budget of incremental updates across all the weight matrices and will overlook the unique importance of different weight parameters. As a result, they say that this is inefficient, so they propose Ada LoRa, which adaptively allocates the parameter budget among weight matrices according to their importance score. Okay, so the important thing right here would be how they create the importance score, I guess. So here's how to do it. They parameterize the incremental updates in the form of SVD, right? Pretty sure you guys know what SVD is. If you don't know, make sure to check out YouTube videos on linear algebra. But with that, uh, okay, so such an approach allows them to prune the singular values of unimportant updates, which is crucial to to reduce the parameter count uh, and circumvent intensive exact as SVD computations. Okay, let's see right here. Such an prune this single values. Okay, right. So that's the approach right here. So Okay, and they conduct a lot of experiments, right? And they say that it's one of the best approaches. Okay, that's good and all. Let's have a look into their GitHub here. Let's see. All right, so it's done by some guy right here. There's the repo, which is nice. Okay, so it's kind of like LoRa, but it right, it has these beta 1 and beta 2 hyperparameters here. Kinda seems like the Atom optimization algorithm, or maybe I could be wrong here. But yeah, regardless though, it's from 2023. Okay, yeah, it's kind of an old approach, I would say. Yeah, but I mean, as long as it works, right? It doesn't matter if it's old or not. So okay, let's not get too deep into that because we have a lot of things to cover here. So this is just gonna be a basic highlight for now. And if there's some interesting approaches that we found along the way, I might go into them in more details if I feel like it. That is okay. So we have IAI tree. infuse adapter by inhibiting and amplifying inner activation. Okay, it's one of those activation methods. Okay, so it's a method that adds three learned vectors to rescale the keys, the values of the self attention mechanism. Um, of the self attention mechanism and the encoder decoder attention layers and the intermediate activation of the position wise feed forward network. Okay, so it does two things: adds the three learn vectors, and it not three things. It does one thing, but it achieves two different types of effect, right? One is to rescale the K and the V of the attention mechanism, and I think it rescales the intermediate activation function in that sense. Right, right. Okay, so let's just copy that. Mm, 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 mm. Okay, so this is another approach right here. Not so sure if it's more efficient than the previous one, but let's have a look here. Okay, so let's copy that. Okay, nice. The abstract from the paper is okay, right. So let's quickly read through this. Okay, few shot in context learning is great because you can do you can force the model to do the things to produce the text that you want it to without retraining it or fine tune it. Okay, and they say that well, this approach, although it's great, right, but it can be better, right? So because you have to reprocess all the training examples every time a prediction is made, right? So parameter efficient fine tuning, right? It is a way of using a smaller amount of parameters, right, for the attention in conjunction to the pre-trained attention weights that you already have. And if you can fine tune those, right, it would be more efficient. So, okay, right. And then compare few shot ICL with a PEFT, and they found that PEFT is much better. So, okay, and along the way, they introduced a new PEFT method called IA to the power 3. Okay, so it's actually to the power 3. Okay, or it's called IA to the power 3. I bet it's something to do in the equations. I bet. So that scales activation. That scales activations by learn vectors. Okay, learn vectors. Okay. All right. Attaining a stronger performance while using a tiny amount of new parameters. Okay. A new recipe based on the teaser model called TPU that can be applied to new tasks without task-specific tuning or modification that validate the effectiveness of TPU on completely unseen tasks by applying it to the RAF benchmark, attaining superhuman performance, outperforming the state of the art by 6%. Right, and the code is available. Okay, so let's see how they implement this. Okay, here it is, right here. Okay, so where is the... Wait a minute, Where is it? Okay, right, so you have to define it here. Oh, what about this one though? This one looks ordinary to me. It doesn't look like something for IA to the power 3 model. Um, okay, perhaps if I want to try to test it out, maybe I should go for this one. Okay, right. So, all right, moving on. Uh, moving on. Oh crap, where is it? Um, all right, is it right here? Okay, maybe I should go back to. Okay, something wrong. Let me just go back to here. Where's the methods? Ah, okay, right here. Cool. All right. Next, we have the llama adapter. Now, I heard of this before, but I didn't pay too much attention to it because it isn't that as popular as LoRa and QLoRa. But that's okay because I'm gonna learn it right now. So okay, llama adapter is a it's a method designed for turning llama into an instruction following model. Ah, okay, right. I see. It's that one. Okay. So okay, the first frees the llama model and only a set of adaptation prompts prefix to the instruction to the input instruction tokens are learned. Okay, right. So imagine if you have like a bunch of like tokens, right? That corresponds to your text, right? To your text data. And on the left hand side, I don't know if it's here for you guys or here, probably here, right? Okay, so on the left hand side of the input, you specify a set of learnable tokens, right? And it, and that's exactly what they try to do here. So it's something, if I'm not mistaken, this is something like a prompt engineering, but not quite that, right? Right, because like you freeze the entire model, and that avoids the need for creating new weight matrices for the entire model, right? You just have to find the right configuration of the learnable tokens, right? And and the hypothesis is that there exists a set of learnable tokens that can improve the model's performance for a given task. And this is what they are trying to do here. So if we copy that, okay. All right, since randomly initialized modules inserted into the model can cause the model to lose some of its knowledge, right? Llama adapter uses zero initialize the attention with zero gating to progressively add instructional prompts. Okay, so this is a very cool approach. Let me just highlight this. Try this out. Let's try this out. No need, um, no need new weight matrix, right? No need new weight matrices for LLM, right? Learnable prompt, learnable tokens. I wouldn't call it prompt. Learnable tokens. Okay, so that's that. Okay, so let me see. Okay, so it's a lightweight adaptation method to fine-tune llama. Okay, by using some SFT data, right? They only use an additional 1.2 million learnable parameters upon the frozen 7B model. All right. So okay. So yeah, so the description is exactly the same as the above. And let's see what about the code, right? Is the code simple or is it like difficult in some way? Okay. Okay, it has been transferred to this link. All right. There's a lot of stars for this repo right here. Oh, and they got accepted in this year's ICLR conference. Great job, guys. Great job. Um. Okay, right. So I would probably try this out. Yeah, I would probably try this out. This will go into my wish list right here. So, yep, this is a very good way. All right, moving on. Moving on. We have LOHA. LOHA. LOHA stands for low rank Hadamard product, right? So, what is a Hadamard product? Well, I know about this, but let me just recap it. Okay, right. It's basically just element-wise multiplication of matrices, right? Pretty elementary. So, okay, it's essentially LoRa, but it approximates the weight matrix with more low-rank matrices and combines them with Hadamard product. Okay, right. Essentially, a very crude approximation. I wonder if it's going to work that well, honestly. Okay, but nevertheless, let me just copy this. Okay. Okay. So it's LoRa, but it approximates that. Okay. Is LoRa is LoRa, but it makes more approximation. That's fine. Okay. So they propose a. Okay. Wait a minute. What the heck? Wait. This is the right paper. Okay. Right. So they propose a communication efficient parameterization, FET para. The federated learning to overcome the burdens on frequent model uploads and downloads. Their approach parameterizes weight parameters of layers using low rank weights, followed by Hadamard product. Right? Compared to the usual approach of LoRa, their approach is not restricted. Okay, so it's not restricted to low rank constraints. Uh, right? Therefore, it has higher capacity. This property enables it to achieve comparable performance while requiring the 3 to 10 times lower communication cost than the model with the original layers, which is unachievable by traditional low rank approaches. Okay, so we're just going to copy that. Okay, right. And they say that their efficiency of the approach can be further improved by stacking it up with other efficient FL optimizers. Okay, right. So I'm gonna be honest here. I'm not too sure. I'm not an expert in federated learning. Like I heard about it before, but I wasn't that interested. But it's pretty useful if you want to deal with real world stuff, right? And it's probably something that I have to learn as well here. So federated learning is a collaborative learning. Okay, right. I see. Yeah. I I remember back in like I don't know like a couple of years ago when the Hugging Face team decided to train their newest model back then. I think it was called Big Science, right? And and it asks the open source community people to contribute their how do I say their GPUs, right? But but it's all fragmented across the world. So one approach to achieve building the model up from scratch is to use federated learning right here. In this case, it's a decentralized approach for training ML models, and it doesn't require an exchange of data from the client devices to global servers. Instead, the raw data on each devices is used to train the model locally. Wait, hold on. Okay, okay. You know what? Forget about what I said just now, but anyway, about the Hugging Face teamwork thing, right? Right. It's something like this, but it's not for consumers, right? So okay, right, right. So all right, everything sounds good here, right? It's just another version of LoRa, right? Let's have a look at their code. Okay, so you basically okay, right? This is for the diffusion model. Okay, diffusers and PEFT right here. Okay, conflict T. Okay, specify the configuration. Yep, just like Laura. Really? Okay, I might have to try this one out. But not so sure. Hmm. About right. I'm not so sure about what to not so sure about in this case. Okay, right. Next we have LOKR. Lork. Is it how you say it? I don't know. Okay. Low rank chronicle product. Okay. There's another kind of LoRa. Okay, which approximates the large weight matrix into two low rank matrices and combines them with the chronicle product. Wait, is this from the same paper as the previous one? Right. So essentially, we have one that is like, oh, let's use Hadamard, and this one is let's use Chronicle. Okay, right. Yeah. And for those of you who do not know what Chronicle is, let's look it up. It's basically this symbol right here. So what you basically do is quite simple. You let me find an example right here. Let's see. Yeah, this is a good one right here. So basically, what you do, right? Maybe this one right here. Yeah, this one. So basically, if you have like two different matrices, right? Let's say A and B, right? So if you do it that way, right? A times B using chronicle product, you essentially, right? If you imagine, right? If you focus on the matrix B, and then you take the matrix A, right? And you put it on the first top left value of the B matrix, and then you you perform multiplication on each every value of the A matrix, right? And essentially, you have a bigger matrix, and now you repeat the same thing for the rest of the B matrix values, right? So essentially, your matrix will become much larger in that case right here. All right. So let's copy this. Okay. Much like Loha, much like Loha in spirit, right? So it's just this. Oh shit. Oh, I didn't mean to curse. My bad. Uh, right. Okay. Okay. Yeah, this is the pain of doing YouTube videos, is that you don't want to like leak out too much stuff that's personal on the computer. Um, okay, what do you have here? Laura. I believe I don't need to go through this since it's really popular, but I'm just gonna like copy and paste the entire thing. Yeah, it's mandatory, I say. So I'm actually quite surprised that I think they should probably put Laura at the top, since it's like the de facto way of doing efficient fine tuning in this day and age. Okay, so this is like the this is like the mother of all approaches so far. Okay, let's take a look at X Laura, the X rated of Laura. I'm just kidding. But right here, oh, okay, it's a mixture of Laura experts. How nice. Okay, so it's like MOE, but for Laura. Okay, it creates a sparse and dense mixture of Laura experts based on high granularity scaling matrix, token layer, and sequence. By using frozen LoRa adapters and a frozen model to drastically reduce the number of parameters that need to be fine-tuned. Hmm. I wasn't sure about this. Okay, let's just copy this for now, because to say it's all frozen, what do you mean? What are you trying to fine-tune in this case? Are you trying to fine-tune like a gating network or something? So let's see. This. Okay, let's copy this. Nice. All right, let's go. Okay, so it's versatile. It can be applied to any transformers model with LoRa adapters. This means that despite MOE strategy, there's no changes to the code. Yeah, because you're just replicating it, right? I think. Okay, the below graphic demonstrates how scaling change for different problems. This highlights the activation of different adapters as generation progresses and the sequence create new contacts. Right here, in this case, tab protein properties or design, strength calculation, force deformation, de novo protein design, and on the left we have some biomaterial science right here. So LoRa layer, gating valve. Okay, I knew it. I knew it. You're trying to fine tune the gating value. In this case, keeping everything frozen except the gating network. I think there must be a gating network here. You're you're just doing that, right? So, but at first you need to get the adapters, which you have to fine tune on something, right? And then you keep it frozen. I'm not too sure. I'm not too sure what this means. Um, okay, but maybe the abstract will say something here. Okay. Um. Right. So they say starting off with a set of pre-trained LoRa adapters, and their gating strategy uses the hidden states to essentially allocate um, which adapter or which layer to be used, right? Allowing the model to essentially be more capable, be more versatile. I mean that's what MOEs do essentially. So okay, let me just copy this and hmm, oh boy, okay, right. Like yeah, like I knew it. You're just fine tuning the gating network. Okay, right. It's inspired by nature, blah blah blah. I mean, not there that I care of. I mean, it can be from like anything really. In, right. As long as it works, it works. Okay. So and to say that, well, yeah, it is pretty good at. It might as well be AGI at that point. It can do bio, mathematics, physics, blah blah blah. Right. It can do a lot of things here. But what I'm interested now is to code. Okay, right. So essentially, just define the adapters that you have, right? I would assume that the adapters will have to be trained on different types of. Will have to be first fine-tuned on different types of data sets. Probably one for bio, one for chemistry, one for physics, one for pure mathematics, applied mathematics, and so on, right? And you can have a set of them, and then you just fine tune the gating network. But I felt like this is not that useful to me since I'm not dealing with this sort of stuff here. But you know what? I'm just gonna take a screenshot of this. Are you watching? Okay, good, very good. So I'm just gonna take a screenshot of that and then placing it right at the side. Okay, very nice. Very, very nice. Okay, let's move on now. Lycoris. Oh, what is this name? Sounds like a disease to me. Okay. Wait, hold on. Just give me 1 second. Uh, what is going on here? Okay. Wait, I'll, I'll do that later, but let's have a drink now since we're talking nonstop. Okay, so we have like a lot more to go. Oh, crap. Okay, so, okay, Lycoris. LoRa beyond conventional methods. Other rank adaptation implementations for stable diffusion. Okay, so it's basically LoRa, kind of like LoRa adapters that modify cross tension layer of UNet. So if you don't know what UNet is, it is basically a type of convolutional network that's typically used for like well, historically it is used for like biomedical stuff. So what you can see here is that you have like um, uh, you have like a sort of like residual operation going on down under there, or maybe I should say at the top there, right? So essentially, you're like compressing the information over time, and 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 at the bottom there, you are decoding out the small information into larger and larger vectors of information. And then what you do is that hopefully that thing at the bottom middle there, hopefully that tensor there would encapsulate the important information, right? And it works pretty well for image recognition and things like that. So okay, let's see. Deloha and Loker methods inherit from the Lycoris classes here. Okay, interesting. So so those two previous approaches, the Lohar and the Loker, are subtypes of Lycoris. Very interesting. All right, and I don't see the implementation being that. Yeah, I mean, yeah, it doesn't look friendly, user friendly at all to me. But okay, okay. I would just take note of this approach and probably not use it, I guess. But some of you guys might go ahead and try that out. But there's a lot more that I have to go through. So yeah, and it's especially for UNet, which I'm not using right now, which I'm not dealing with right now. I'm dealing with LLMs. So let's go to the next one, shall we? Okay, so multitask prompt tuning. Now, here's the fun stuff right here. Multitask prompt tuning decomposes the soft prompts of each task into a single learned transferable prompt instead of a separate prompt for each task. Okay, wait. Let me get this right for a second here. So, okay, multitask prompt tuning. Gotcha. Why did I delete the layout? Why did I do that? Okay, right. Multitask prompt tuning. Let's go. So it it splits the soft prompts of each. Okay, right. It decomposes the soft prompts of each task into a single learned transferable prompt. So it's like a unification into a single prompt, right? The single learn prompt can be adapted for each task by multiplicative low rank updates. Okay, so you do have to have like another set of operations just to convert that general learn prompt into something that can be used for a specific task. Okay, so okay. So prompt tuning, in which a base pre-trained model is adapted to each task via condition on learned prompt vectors, is interesting, but they typically have to learn the soft prompts from scratch. Okay, and it's not clear how we can like exploit the rich interrelated knowledge between the different types of tasks. Right here, and that's the uh, question that they are trying to address. They have this multitask prompting approach, which helps out. Okay, so let me go through what they have here. Okay, so they do have a class here and another class there. Um, Still, right, not much documentation going on here. Should I use it? Should I? Do you guys think I should use it though? Yeah, I don't know if it's gonna be more efficient. Should I? Should I? I will have to think about it after this video. Okay. Let's go through OFT. So stands for orthogonal fine tuning. It's a approach for adapting text to image diffusion models. Works by reparameterizing the pre-trained weights with its orthogonal matrix to preserve information in the pre-trained model. To reduce the number of parameters, it introduces a block diagonal structure in the orthogonal matrix. Okay, right. So let's have a look into this. Sounds pretty cool. Orthogonal fine tuning. Okay, right. Works. Okay. that. All right. Large text to image models is pretty good in generating images from text. Okay, how to effectively control these models is quite problematic. To do that, they introduce OFT. Okay, so OFT can probably preserve hyperspherical energy, which characterizes the pairwise neuron relationship on the unit hypersphere. They found that this property is crucial for maintaining the semantic generation ability of the models. To improve that, to improve fine-tune stability, they introduced constraint OFT, which has some radius constraint to the hypersphere that they are using originally. So they consider two important fine-tuning text-to-image tasks: subject-driven generation, where the goal is to generate subject-specific images, given a few images of a subject and a text prompt, and a controllable generation, where the goal is to enable the model to take in additional control signals. Okay, and they show that it works better than the other methods, which everyone always say that in their paper. I mean, yeah, this approach sounds really nice, but since it's quite tailored for text to image, which is not what I need right now, I will probably skip that. Mm. And now we have the next one right here called orthogonal butterfly. Orthogonal butterfly. It's BOFT. BOFT. BORF. BORF. It's BORF. Okay. So it's used to fine tune foundational models. Okay, good. Now we're talking. So it improves upon the previous OFT approach, right? By using fast Fourier transform. Okay. So okay, so this is an improvement over that. Butterfly orthogonal morph. Yeah, okay, let's go. Mm-hmm. Yeah, and the code looks fine. I guess. Yep, everything is in here. Pretty good. All right, so let's go through the next one called polytropon. Polytropon. What is this? It's a okay, right. So the next one is polytropon. Right here, polytropon. We okay, right. A multitask model with a number of different LoRa adapters in its inventory. Okay, it's kind of like the mixture of LoRa experts, but I guess this one has more of it, more experts, more adapters. Okay, so the model learns the correct combination of adapters from its inventory with a routing function. It's the same approach as the MOE. Okay, a gating function or a routing function that chooses the best subset of modules for a specific task, right? It also supports multi-adapter routing, a kind of routing mechanism which builds and improves the routing function by combining the adapter hits more granularly. Right, the adapter hits are separated into disjoint blocks, and a different routing function is learned for each one, allowing for more expressivity, or should I say accuracy in this case. Okay, so there's two papers right here. Oh boy. Oh boy. Yeah. So this one is yes, yeah, it's kind of similar to the MOE. All right. So this one, it's roughly it probably belongs to the same family of tree, the tree family with MOE. So mm, so that's that. Right. Oh, okay. Let's take a look at the abstract here. Okay. A modular design encourages blah 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 blah. Okay, right. That's a lot of fluff right there. Oh man, that's yeah. I don't think it's that important for us to. Okay, wait, right here. I guess this one is important, not that one. Okay, polytropin jointly learns an inventory of adapters. So you basically have a stockpile of pre-trained adapters, and you have a routing function that selects a variable size subset of adapters for each task for both pre-training and few-shot adaptation. In this paper, they investigate the role that the adapter routing plays in. All right, so this is a better way of describing polytropon. Okay, so the proposed multi-head routing, which combines the subset of adapter parameters and outperforms poly under comparable parameter budget by only fine-tuning the routing function and not the adapters. Okay, all right. Okay, how about the code? The code looks, hmm, yeah. There's not much in the code, documentary, but whatever, right? Um, I don't think I'm gonna use that anyway, but it's good to know, guys. It's good to know. All right, moving on, we have P tuning. Wonder what that is, right? Wonder what that is. So P tuning. Okay, so it adds trainable prompt embeddings, learnable prompt embeddings to be exact, to the input that is optimized by a prompt encoder to find a better prompt. So you don't have to design appropriate prompts. Do you know what? Do you know what here? Right? If I couldn't find an appropriate right, if the reinforcement learning algorithm is like right is like terribly slow, right? I might have to go for this one right here. Like, man, it's like really bad. Like, it's gonna take weeks. It's gonna take months, and by that time, I I wouldn't be able to graduate at all. So maybe P tuning can save me from this misery, right? But yeah, okay. I think you guys know what P tuning is, right? But I'm more interested in the implementation here. So okay, define a config, and that okay, pretty simple, pretty simple. I'm gonna highlight this. I'm gonna highlight this. Use this if RL is too slow. Yeah. Can you believe it, guys? I spent like 1 or 2 days just to create the RL system, right? I mean, not really creating, but like incorporating it into my script, right? And now you're telling me that I should have probably and nature is telling me to like use P tuning, prompt tuning. Yeah, maybe I should have done it in the first place, but you know what? At least I learned something. And that's what life is all about, really. That's what life is all about. You make mistakes, well, those are mistakes since I'm a student, right? And I get to like learn about a lot of things by making a few mistakes along here and there. Of course, it's unintentional, but yeah, whatever. Okay, right here we have prefix tuning. Have I? Jeez, I'm hungry now. Here. Okay, prefix tuning. Oh, we are almost there. We are almost there. That's good. Prefixes a series of task-specific vectors to the input sequence that can be learned while keeping the model frozen. The prefix parameters are inserted into all model layers. Okay, now this is a funky way of doing fine tuning. So right here, right? So instead of updating all the model parameters, right, you simply just okay, keep all the model parameters frozen, but you just optimize a small continuous task specific vector. So it's called virtual tokens, and they tested it out on GPT-2 and BART. Okay, which year is this paper from? Which year? Which year is it? Which year is it? Let me find it. It must be pretty old. Yep, yep. It's like almost 4 years ago. Mm, But you know what? It does make sense. It does make sense. Old is gold. Old is gold. Really. Like the simplest way could be better. It could be better. Oh man, yeah, I'm gonna have to try that out after this video. All right, we are almost there. Yeah. So prompt tuning. Okay, prompt tuning. Then what's P tuning in that case? Isn't it the same, right? But anyway, they call it prompt tuning, which is another kind of method, right? That you add task-specific prompts to the input, and those prompt parameters are updated independently of the actual pre-trained model parameters, which are frozen. Okay. So right here, let's do that. Let's have a copy here and here. Okay, right. All right. Let's go through this abstract one more time. So in this work, we explore prompt tuning, a simple way of learning soft prompts. In this case, it would be just like the previous methods, right? You have like a set of learnable vectors, right? But in this case, it's the vectors will be used as those soft prompts, right? During the input sequence, in the input sequence, right? So, okay, to condition it on specific tasks. Unlike discrete text prompts, soft prompts are learned through back propagation. Yeah, we know that. Yep, and that's that. And and it's pretty okay. Yep, there's quite some stuff in here. Yeah. I mean, it's all right. It's all right. It's all right. It's just like the previous one with some minute differences. It's okay. It's okay. I will give it a pass. I will give it a pass here. Okay. Oh crap! I show my desktop again. How careless of me. Oh no. I wonder if someone in my audience is gonna do some bad stuff to me after seeing that. Oh no. Oh no. Okay, so I'm just gonna copy and paste this right here. Maybe I should like put like a big black picture in the desktop and then like no one is will be able to see anything in my computer apart from these papers and websites here. Now, this one is a pretty interesting approach here. which actually convinces me to make another video right now. It's this one, this approach called layer norm tuning. So what this basically is like you just fine tune the layer norm instead of doing like low rank adaptation approaches, and it's yeah, and it's ridiculously efficient, right? And it's ridiculously efficient because you are only fine tuning layer norm, right? You don't actually have to like do anything to the attention weights and things like that. Yeah, so I was like really hyped for this approach uh, until now. So where's the paper? Where's the paper? Where's the paper? The paper is right here. Tuning layer norm in attention. Right. It's released last year, December, which is okay, but it's kind of old. Right. So this is the paper right here. Initially, I was thinking like, oh yeah, maybe I should cover this paper, but then I thought, right, I should probably cover like all the major approaches, just like what I'm doing right now, right? So that I can at least know what kind of approach I should go into a bit more for my own research, right? For my own PhD work. Yeah. So the efficiency is ridiculous in in here. Yeah, pretty good job with this, and I'm gonna use it. Thanks a lot. So let me just copy this. Um, tell you what. Okay, which only fine tunes that. Very efficient, right? Right. Very low params. Only like under 0.01% of the params. Yeah, they should probably mention somewhere here, like how low number of parameters you're fine tuning. Yeah, I'm gonna use it. I'm gonna use it. Okay. Oh, okay. We have reached the third last thing to cover here. Okay, this one is called Vera, vector-based random matrix adaptation. So it's another LoRa. It's another LoRa. It doesn't get more creative than that, but it requires even fewer extra parameters while achieving about the same performance. Okay, very good, very good. Oh, very good, very good. This is very good. Thank you so much, my lord. Thank you so much. But I don't think it's gonna be as efficient as layer norm tuning. Probably more accurate than layer norm tuning. Probably, but I really don't know. I have to try them out here. Um, okay. The reduction of the count of just say the reduction of trainable parameters is achieved by sharing the same low rank matrices. Okay, by sharing the same low rank matrices across all layers and then training only two additional vectors per layer. That's insane right here. So that's even crazier, right? It's like it's unlike the previous approaches, which is like, oh yeah, we can like get this like even smaller matrices and then like combine them or something using Hadamard operation. In this case, right here, do you know what? Screw that. We just use the same thing over and over again, but of course we need to have some variation to each layers. So you will have to use two vectors, the two additional vectors per layer. That's what they are going for in this case. So okay, nice. Wait, hold on. Let me check the implementation. I got to say, pretty neat. I like this. Approve. Okay, next. Yeah. So I'm just gonna try this out. Yep, yep. Okay, this one. Try this out. Try this out. Nice. All right. The second last approach is Fourier fine tuning, discrete Fourier transformation fine tuning. Okay. So it's a so it uses discrete Fourier transform to compress the trainable weights. It outperforms LoRa while using less parameters. Okay, outperforms LoRa, higher accuracy, less parameters. Okay, okay, I'll 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 take that. I'll take that. Okay, I'll take that. I'll take that. No problem. No problem. No problem. Right. No problem. There should be no problem. There should be no problem. No problem. No problem at all. There should be no problem. Nothing. Okay. Alright, here's some bad news here, I suppose. So the following constraints are only linear layers are supported. No, why? Quantized layers not supported? You got to be kidding me. I bet this is why this approach is not even that popular in the first place. It's because it doesn't support quantized layers. Ah, what a shame. What a shame. Damn it. Okay, but look at this amount of trainable parameters. It's so tiny. So tiny, but at the same time, if I have to use this, I'm gonna use it. I'm gonna have to fine tune it unquantized, which I can't do. Oh, damn. What a shame. What a shame. Okay, so, man, this is what life is. This is what life is. And I'm not mad. I'm not mad. I'm not mad. It's just a shame, really. But anyway, moving on. We have vector bang LoRa, extreme parameter efficient fine tuning with vector bangs. Let me guess, a bang of adapters? Probably not. But okay, so it extends LoRa by learning a fine-grained parameter sharing scheme at the subvector level. What do you mean by that? Significant high parameter efficiency. These are things like storage and transmission. Okay, it works by decomposing lower rank matrices for different layers and modules into subvectors, which can be shared through a vector band. Okay. Yeah, sounds pretty interesting, but I don't think I will be using that, unfortunately. So, but I will just keep on reading through it. Okay, right. So as the adoption of LMs increase, the need for per user and per task models customization increases, right? So PEFT and LoRa and stuff like that, right? It incurs substantial need for storage and transmission. So there's this approach called divide and share paradigm that breaks down barriers of lowering decomposition across matrix dimensions and modules and layers by sharing the parameters globally via a vector bank. Hey, I tell you what, how about instead of doing this, you can use Vera, right? You can use this approach right here, right? Because like you only need like a single a single what is it called? suddenly got a brain freeze right here. Yeah, just use this one right here. Just use this, right? You essentially share the same low rank matrices across all layers, right? And you probably don't need this, right? I mean, unless you have like a lot of users, then probably you're gonna need to use this and then like share it in the vector using the vector bank. Yeah. Okay. Right. Yep. And they use a differential top K module right here, probably for selecting which vector to use, I think. But yeah, so that's that. All right, cool. And now it's all done, right? Like there's like a lot of approaches here. I think there's like 20 different approaches, right? So I'm just gonna say 20 types of what should the video be called? Um, 20 types 20 types of methods for fine tuning of parameter of PEFT methods, right? On the Hugging Face. Right, so that's that. Okay, wait, hold on just a second here. Probably time for lunch. Just give me 1 second. All right, I'm back. So right now we have all the things that we need on Hugging Face, right? Right. So I would say that the ones that I'm interested in is probably things like llama adapter and yeah, and I might try some variations of low rank adaptation approaches. Um, yeah, so I guess yeah, I think I might just have to like skip RL entirely since it's not that efficient. But yeah, I mean, yeah, make sure to like, comment, and subscribe. And yeah, and thanks for staying with me along the entire video, right? Because like no one actually does that, I know, but it's good to show like the actual process, right, of learning new things, and it's kind of keeping me like motivated to like go through like every single thing. Otherwise, it's pretty hard, Yeah. So yeah, but I really do enjoy the process of making these videos right here. So yeah, I will, yeah, and make sure to check out my Patreon as well if you want to support these videos or my PhD research. But yeah, thanks a lot, folks, and I will see you guys in the next video. Probably not gonna be like after 2 weeks, probably in another few days, right? So yeah, bye. Stop recording. Bye.